Hi, I'm Mingfei. I'm postdoc researcher at Microsoft Research Cambridge. I'll be hosting this panel discussion today. And today we are going to discuss the generalization in reinforcement learning. We have seen tremendous applications of reinforcement learning in recent years. We all know that reinforcement learning has been successfully applied to complex video games and achieved superhuman level performance. We have also seen that as the training of reinforcement learning scales up, and we could also train multiple agents that learn how to cooperate to complete really complicated tasks. Today, we are going to have a discussion on how reinforcement learning could be further generalized and why generalization matters in reinforcement learning for the time being. Joining with me for this discussion today are four panelists: Cheng Zhang, Harm van Seijen, Roberta Raileanu, and Wendelin Boehmer. Before we get started, let me first briefly introduce our four distinguished panelists. Let me take the alphabetic order and start with Cheng Zhang. Cheng is a principal researcher from the Machine Intelligence Group at Microsoft Research Cambridge. She's generally interested in machine learning and computer vision. She's also working on representation learning and approximate inference with Bayesian theories. Our second panelist is Harm. Harm is a principal research manager who is leading the reinforcement learning team at Microsoft Research Montreal. Harm and his team are focusing on fundamental challenges in reinforcement learning, including transfer learning, continual learning, hierarchical approaches for reinforcement learning, and multi-agent systems. Welcome, Harm. Our third panelist, Roberta, who is a PhD student from New York University. She is interested in designing machine learning algorithms that can make robust sequential decisions in complex environments. Her interest spans a wide range of topics in reinforcement learning, including exploration, fast adaptation, and multi-agent learning. She's also interested in understanding and improving the generalization and robustness of reinforcement learning agents. Welcome, Roberta. And as our fourth panelist, also the last one, Wendelin, is an assistant professor at the Delft University of Technology. He's interested in the intersection between inductive and deductive reasoning in artificial intelligence. Wendelin's research focuses on generalizing reinforcement learning by deductive reasoning, which could be structural constraints like graph neural networks, adaptive constraints like attention mechanism, uncertainty reduction like on-sample estimates, and distributed learning like multi-agent reinforcement learning. Welcome, Wendelin, and welcome all of you to join this panel discussion. As we are discussing generalization in reinforcement learning today, can I ask all our panelists the first question? What do you think is a generalization in reinforcement learning? Or like when we talk about generalization in reinforcement learning, what do we really mean here?
Generalization in RL means that the agent is not trained and tested on a single task, as is typical the case in reinforcement learning, but it is tested on a set of tasks. It's trained on a set of tasks and tested on a different set of tasks. And in the default generalization setting, the training and test set come from the same distribution. And the main challenge is to get good test performance while using a small training set. So in order for this to work, there needs to be some underlying structure for the distribution. And there is all kinds of different structure possible. It could be the case that each task consists of the same environment, but there is a different reward function. Or it could be the case that all tasks are very similar, but have different irrelevant features. So there is many different dimensions of generalization.
I agree with Harm
cool.
very much. I agree with Harm very much, and I think generalization is a really broad concept. But I would say it's not only in reinforcement learning, but it's for the whole more general machine learning community, right? So how to define generalization? So is just to generalize to a different random seed is generalization. I think even for the definition of task, I think that is also very, people have different understanding. Does it mean like, for example, the goal, like how you shape the reward will be different in reinforcement learning? And also does just the kind of the dynamic is the same, but kind of just the background color change a little bit. So I think in reinforcement learning, different from many other machine learning task. It's just there's more concepts there. And I think generalization also ranging from just a really small, from a different random seeds to different new environments to completely different goal. So I think that's a really big space to do researching.
Yeah, so I would I'm agreeing with both of you actually, but I would like to point out more that there are more constraints on the concept of a task. And that's because if we are talking about generalization over different tasks, then we quickly get into this area where we're talking about tasks that are completely different from each other, which you literally can't generalize over because you have no idea what to do. And so I would add here that one important distinction in is zero-shot generalization versus few-shot versus many-shot generalization. And the most obvious one is the zero-shot case, in which you simply shown something that you haven't seen before and just ask to react to it. And if the reaction makes sense, that's good. If not, not. And the distincting feature here is the indistribution, where you think, what have you seen during training that you think you can generalize over?
Yeah, so I also agree with everything that's been said so far. I think something I find sometimes useful when trying to think of generalization in reinforcement learning is trying to think of the different parts of the MDP we're trying to generalize over. As I think Cheng also mentioned, sometimes we want to generalize only over different observations, but perhaps the underlying state is the same. Sometimes we want to generalize over different dynamics, where typically we actually require some interaction with the environment. So it's very hard to do, I think, zero-shot generalization in that case, as Wendelin was also mentioning. I think there we need to interact a bit with the environment and hope that we can do some kind of few-shot generalization or adaptation in that case. And similarly, perhaps an even more challenging setting is the one where we're trying to generalize to say new reward functions, or say completely new goals in some sense, where we really need to leverage some kind of common structure of previous tasks you've seen. And just another thing I wanted to mention, I think, is also the setting of generalization in reinforcement learning is also quite different than, say, supervised learning, because here sometimes you even need to generalize within while trying to learn a certain task, because as you're exploring the environment, the data distribution is changing. So you need to sort of figure out how to relate new states or observations to previous ones you've seen. So it's more like a continuous way of generalizing rather than a very clear separation of training and test, I would say.
Okay, it seems like the generalization in reinforcement learning covers a huge range of different topics, and some of these topics, as far as I know, has been for example, at least studied for years, right? Like one-shot learning, all these representation learning here. So then, why do we care so much about generalization today? I mean, or why does generalization matter for reinforcement learning for the time being, given that we already have a bunch of different reinforcement learning algorithms, either on policy or policy, and the algorithms which can scale up. So why do we care the generalization in reinforcement right now? I know Harm, you're also leading the team in reinforcement learning. You also have been studying this topic for many years. What's your opinion on this question?
I mean, generalization in RL, I think, is important for the same reason it is important in supervised learning, which is that if you want to apply it to the real world can be hard to predict. You know, it's not stationary, and it's hard to predict exactly what you're going to encounter. So in order to get good performance in real world applications, you need to be robust with regards to various changes. I think so. So that's the main reason, and so that's the reason why generalization is important. So then the question, why is it important today? Why are people focusing on it today? I think that has to do with, reinforcement learning is fundamentally a much harder problem than supervised learning. So for a very long time, even getting good performance on single tasks can be very challenging. So for a very long time, people have just been trying to push the boundaries of trying to solve more and more difficult problems. And I think in the last couple of years, there's been quite some successes with that. A lot in the games area, the Atari benchmark, even solving Go. So these are very impressive examples, and I think that generated a lot of interest and attention from companies like Microsoft and others as well. And so then the natural question is, we have these very powerful RL algorithms. Can we now build powerful applications that use these powerful RL algorithms? And I think that translation is not necessarily very easy because of these shortcomings, like the gap in generalization. So I think that it's only natural to then that now people focus on trying to solve these gaps such that we can apply it in various real world scenarios.
Yeah, I like the kind of like. Yeah, go ahead, please.
Yeah, so I just say that's exactly what I wanted to comment on this topic as well. But I just want to mention, like, for example, some application scenario, like, for example, healthcare, for example, education. So I think these are the scenarios that can be socially very, very impactful. I think as a whole machine learning community, we are kind of aiming more of this, how can we really help the society more? And this as application, not only generalization itself is required, right? So because we're not in a single simulator, because one game is like a single simulator, like we require generalization. But another thing I want to think a little bit about the cost. I mean, one, it's not generalized. I mean, we can kind of don't care about the cost in some way, but think about in healthcare setting. If you want a reinforcement learning aided AI system to help in some decision making in the healthcare, let's say you can train one agent per hospital. But then with generalization, if your algorithm can fully generalize, you can also enable the possibility to utilize more data in some way, like to amortize the whole training, right? So that's also a more efficient use of data. And I just think about I also want to bring the topic. It is definitely application driven, but apart from multiple environments in real world application in some way like this. And another thing is the cost for data acquisition can be much, much more in a simulation environment. And that is something we need to be aware of.
Okay. I think that problem also exists in other, like, for example, machine learning topics, for example, meta learning or even supervised learning, right? For example, when we talk about the healthcare AI, how can we apply the machine learning there? So we also have this generalization problem there. So it seems like to me, these problems are not specific to reinforcement learning, right? It's kind of a general problem to all the machine learning topics.
That's definitely true. Go ahead. I just want to say I agree very much, but I also say that for the question why does generalize measure in reinforcement learning now, we can swap two things. One is we can swap reinforcement learning with many other research direction, and the second thing is I think we can almost swap generalization to many other things, like we can say fairness, privacy. So everything relates to one deployed machine learning system in the world, apart from the accuracy or in some way a performance-driven metric. We care about all other metric. I think it is of great importance now at the same time.
I somewhat disagree with that statement, which is good because we have to disagree on something. So first of all, there are some clear distinctions between reinforcement learning and supervised learning. For example, one wrong decision in a supervised learning example, classifier, for example, is one wrong decision. But a wrong decision in a reinforcement learning agent means that all of the successive decisions can be completely down the drain. And this sort of goes into into Cheng's argument about data efficiency, that in, for example, partially observable environments, it's not sufficient to just observe a current state. You have to observe the entire trajectory that led to that current state, which then means that just for data acquisition, if one thing changes, you have to re-record the entire data stream because one thing has changed, therefore all of the history that could come to lead to this one point could have changed. So we are like in a situation where we require way more data, like data sampling to be specific, which is fine in large games like in Atari and in StarCraft. This is all there, it works perfectly. But this is because what we're basically doing in machine learning is we're distilling all the experiences that the agent has seen during its lifetime into this neural network. And then we hope that that neural network has seen enough data to generalize over it. But this is an actual problem when we apply these things in real life. Like Harm said in his introduction, in real life, there can be like tasks where the unimportant background things change. Do we really want to sample through all of those samples? Probably not. And so I would kind of say that why is generalization and reinforcement learning particularly important right now? It is because it's the cornerstone that will make reinforcement learning applicable in reality, not just in simulations in computer games, but in actual hospitals.
I just want to clarify that games I consider real-world applications as well. If you have Xbox games, for example, there's a lot of exciting things you can do there. But also, for efficiency reason, if you're a developer, you want to have an NPC that is trained with reinforcement learning. So the game changes during development, and you can't retrain from scratch each time you're NPC. So for efficiency reasons, you want some generalization behavior. But yeah, I mean, Xbox games, there's a lot of money involved in that, and that's very much a real-world application as well.
Yeah, I mean, except those game applications, do we also have other applications like in which the generalization in reinforcement learning plays a kind of crucial role there?
I think healthcare is something we talked about. I just want to mention, education is another thing, and my heart is close to, where like it's a similar setting. There are different schools, and definitely, I mean, children are the future. If we can help using AI systems for personalized decision making for children's education, that would be fantastic, and that definitely requires generalization.
Yeah, I see. Okay. So it sounds like generalization could be a big issue when we consider applying reinforcement learning into any like practical applications. Then are there any like benchmark tasks we can consider as a test bed for generalization in reinforcement learning? Roberta, I know you have been working on generalization in reinforcement learning for many years and also recently published several papers. So can I ask one question for you? Like what benchmark tasks did you use for your projects and why you were using them?
Yeah, sure. So these days, I'm quite a big fan of certain types of procedurally generated environments, largely because you can sort of like very easily get a range of very diverse instances of the same task and then split them into training and tests and try to probe generalization. I think it's also nice because you can try to gain some intuition in terms of how many, say, training environments you need in order to get good generalization in the entire space you care about for like a certain complexity of the task and certain sort of like diversity of the things that you're changing in the environment. And a few, just more concretely, I've been using a lot this ProgGen benchmark, which I think is quite good. It also forces you to learn directly from images, so learning good representations and so on. I also like NetHack, which has like a richer world, and you really need to learn to sort of like adapt to different entities and dynamics and so on to do well in this task. I think there's also DeepMind control with distractors, which is sort of like the typical DeepMind control benchmark, but with some video in the background. So here I think the task and like the setting you're trying to solve is a bit more clear. So you're really just trying to capture the elements of the observation that are relevant for solving the task, and sort of like avoid overfitting to sort of other things in the observations. So I think there are quite a few that are sort of decent for probing different types of generalization right now. But I think there's still probably some sort of like parts of the space that are missing, and I would like to see more environments on. And I think in particular, in some cases like ProcGen or NetHack or other environments, it's not very clear what you're trying to generalize over. Because there's so many elements changing, like layouts, colors, dynamics, and so on. So I think it'd be really nice to have certain benchmarks where it's clear what you're trying to generalize over, like say only the dynamics or only the layouts or things like that. And I think it will also be useful to have benchmarks where you can sort of like tune the difficulty of the generalization problem, and perhaps how, say, out of distribution the test environments are and how different they are compared to the training one. So we can measure progress on this task more easily. Yeah, I'd be curious to hear from others, perhaps what else they think is needed in terms of benchmarks, environments, and so on.
Yeah, I think that's a great answer you gave. And yeah, for me, what you mentioned, like with ProcGen, it's sort of unclear what it generalizes over. And yeah, I think having benchmark where you can very clearly specify this is the dimension I want to generalize over, I think that would be very valuable, because yeah, different techniques might be effective for different dimensions. So it might be helpful to, if you have benchmarks that are very clear in what dimension they generalize over, that could help sort of further with making faster progress. And I think ultimately, like, yeah, it should be motivated by what's the real world problem that you want to solve. Do you want to build an NPC for an Xbox game that has to be robust with regards to different types of player behavior? Then you want to benchmark that test for that. And yeah, and so for ProcGen, yeah, they have a combinations of dimensions. So I think that's the, yeah, like it's good to get a general sense, but to develop very specialized techniques that work well for one dimension of generalization, more dedicated benchmarks might be useful.
I would add that to test something like out of distribution generalization, a tool like this would be, again, very useful, because right now we don't really have that. We can basically just define, we basically have just benchmarks that define a specific data set or like a specific task set, and then you can like sample from that. But what would be really useful is if you have multiple dimensions and you can sample like in one dimension and then just like arbitrarily change the other during testing to see how well that particular type of out of distribution generalization generalizes with the method.
Yeah, I mean, like when we talk about the different dimensions to generalize over, like it seems like in practical applications, all different dimensions are actually entangled, right? So we cannot easily separate them. So we have actually so many dimensions to generalize over. So it seems to me it all boils down to like how the methods could generalize from examples, right? No matter in what dimensions you are generalizing actually. Like then how does it just generalization differs from the generalization in supervised learning? I think we also like touch upon on this topic before. I'd like to hear some more opinions on this. Chen, I know you have been working on supervised learning for quite a long time, and also these Bayesian inference theories, right? Based on your expertise and what we have discussed so far, what do you think is like the biggest difference between like these two types of generalization here?
Okay, so now we're discussing difference, but I want to discuss both the difference and the similarity. So first, I mean, in supervised learning, I mean, especially if I like to take a causal view on things nowadays. So like, we think about generalization, what type of shift it can have. It can be changing of distribution, so the x to y. it can be, we call it a target shift, right? So the distribution, the y distribution just shifted. It's like a kind of a different population. But the mechanism, how to generate from x to y, doesn't change. So that's one type of thing we need to generalize from a supervised learning view. Another thing is, how about if the mechanism from x to generalize y, that can also change a little bit. Do we want to generalize that? So in supervised learning, I think a lot of generalization focus on, either this target distribution shift or kind of conditional distribution, which means the mechanism change, or both. So that's it. But as we discussed a lot, reinforcement learning are just a much more complicated domain. We have the whole MDP. There are just more things can change. And so that's just a little bit more challenging task. So I think that's the difference, because I think in the beginning we talked about it already. It's just a lot of things in reinforcement learning can change that supervised learning don't necessarily need to change, because that's specialized in reinforcement learning. But that's the difference. But then I also want to talk a little bit more similarity. So I mean, a lot of technique that I think people develop in supervised learning or unsupervised learning, like just in general, how to model the data, like even deep generative model. I mean, there are a lot of basic technique like noise injection, regularization. I think the same technique can be used in reinforcement learning, and I think it's also important to, I mean, for people, I think this field are kind of evolved but separate, but I think it's also important to get inspired from each other. Like if there is a new technique in supervised learning, I think very, very likely this technique will help in reinforcement learning as well. Maybe this technique solved supervised learning generalization. I don't think that's a solved field, but let's say this technique like kind of make the generalization in supervised learning improve this much, and in reinforcement maybe this much. I think that's also very likely to happen. But I do think it's really important to kind of keep an open eye and constantly get inspired from all different directions. And I also like, for example, personally, I also kind of believe from taking a causality view in supervised learning can really help a lot of generalization, robustness, etc. And I personally also believe that the same view may actually really help reinforcement learning as well. So I think that's my answer. There's difference, but there's also a lot of similarities.
Yeah, that makes a lot of sense. So in terms of like the reinforcement learning, because reinforcement is essentially about the sequential decision making, right? So are there any generalization problems specific to the sequential decision making?
Yeah, I mean, one thing that would be interesting that is maybe different in reinforcement learning, like a lot of the current focus is on the representation, and so techniques can be used from supervised learning. And you just learn a good representation, and then a simple model-free method on top of that is used. But I mean, I can also imagine an approach where the focus is less on the representation and more on a model of the transition dynamics, and then use a model-based approach to find a policy. And I can imagine that for certain modes of generalization, that can be a very effective approach. For example, if you have different objects and the transition dynamics per object is similar across all the different tasks, but the configuration of the objects is different in each task. And if you take this model-based approach, I can imagine that would give much stronger generalization behavior. So I'm interested in seeing, like, the more people work on generalization in RL, we get more and more dedicated methods that are unique to RL that don't make much sense in supervised learning. And I think such a model-based approach is an example of that.
Okay, yeah.
I would add one pretty big difference between supervised and reinforcement learning in terms of generalization, and that's that in reinforcement learning we have, by its very nature, a sequential process. This is very different. In supervised learning, if you make a mistake, you can't really deduce anything for any other sample, because the other sample is IID drawn from that distribution. Who cares if whatever you have now measured as an error would generalize to that other part of the distribution. But in reinforcement learning, we make little steps in our state space. So if you leave the state space that you know, you might be able to kind of like use an ensemble of models that each predict like different parts of the environment, and then just check like which of those models are still accurate here and which are not. And that's something that you simply can't do in supervised learning.
Yeah. Are you saying like in reinforcement learning we have this like specific distribution shift problem here?
Yes, like and we have like specifically, I would say we have like an overfit problem, where the data that you are drawing, like if you're training in like 1 or 10 environments, then the data that you're collecting in these environments will be like specific to the specific circumstances in this environment. So now if you change like the background or you change like, you know, any small thing, you can have like, this can have huge consequences for the solution of the method. But without like training on this variation, you have no idea how these circumstances will look like. So it's sort of like it puts something on top of it. It's not just that you know, sometimes you see samples that you don't know, and then you have to generalize over them. But it's like having like something that you don't know in your environment can lead to changes, like to global changes in your policy, in the optimal policy, that affect all the other states around you. Like I want to give like a simple example. Like let's say you have a robot who needs to go through your house. Normally the robot can just like pass that door, but now you just put some, I don't know, you put a chair in front of the door. So the robot basically now realizes, okay, it doesn't work, can't pass this door. What does the robot do? Well, it can simply move the thing, like move the chair to the side, but for that it probably needs to start exploration again. So you can't just like expect the neural network to do all the work for you. You have to, your algorithm, your execution algorithm has to know that something goes wrong and that it has to relearn something. And that can get even worse if like now there is not a chair in front of the door, but somebody locked the door. So the robot has to go somewhere else, grab the key and come back. Like in this situation, the robot would have to re-explore the entire environment just like to find the correlation between the key and the door. That's also like something that's like none of these problems exist in supervised learning. They all come from the specific sequential nature and from the fact that the solution of a reinforcement learning problem is not given for every state, but it's sort of like a meta problem that sits on top of the things that are given.
So I will say a little bit like it's a decision making. I mean, in some way, you said it's relearns all the correlation. I mean, I kind of personally I feel if a system that is causal aware, that would be just much more efficient. I think that's my point before. So a lot of thinking maybe how to say, not saying supervised learning, but let's say this is a lot in common with one-step decision making. We don't even need to make it sequential. I think it's more like on single step decision making. That is already something we need to solve.
I'm not so sure about that, because basically if you just like, for example, if exploration wouldn't be a problem, so if you would have like some protocol that just like start exploration again as soon as you realize that your current policy doesn't work the way that you expected, then if we would have like single decisions, after a while you would have found the right decision. And if that decision was all you had to do, you can proceed. Like that's not a problem anymore. But in a reinforcement learning setting, basically you can introduce changes to the task that require the agent to basically throw away all of the knowledge that it has collected so far and reacquire everything.
But the key here is like the agent didn't understand finding the key is the kind of the cause and the effect is to open the door. If the agent be able to understand this concept, of course you need to relearn things, right? But you don't need to explore from scratch, because then you know it is, if the key is not here, the target here will be just finding the key, and they know what does the key look like.
Yes. But if it's a model-free algorithm, then the key needed to be like, you need to have tasks in the task distribution that tell you that the key is responsible for opening this door. If you don't have that, there is no, like, the model-free algorithm will simply not learn it. It's different from a model-based algorithm. And a model-based algorithm, like, if you give it enough capacity, in principle, it could solve all of this. But then you kind of ask the agent to learn a sufficient model of the world to do all possible tasks. And I'm pretty sure that everybody who does model-based reinforcement learning would agree that this is not feasible at our current state of the art.
That is very true. I agree very much. I think for this case, for model-free one, everything agree. For model-based one, there's hope. It's just not there yet. But I think that if we're doing the model-based one, I think that's also the space can be easier get inspired from other machine learning directions, which is all not solved problem.
Yeah, I mean, there are like theoretically there are solution for this. This is like this entire strain of literature about like natural playing and like robots who just try to build concepts of the world, just like by seeing how to maximize the entropy of their state space. And those things could, in principle, like allow you to sort of learn submodules that allow you to do all of these things. However, these are things, but then you have to have like sort of a process on top of that, which sort of combines all of these things in the end. And we just say, oh, we're just using model-based reinforcement learning, but that's probably not the solution, because like the idea that you just need a perfect model of the world to predict the world perfectly, it's sort of, I think even the physicists have sort of let go of that.
Yeah, the interesting observation here really seems to be that we seem to be on the same page that model-based RL is maybe more suitable for generalization. Nevertheless, all work in generalization happens with model-free RL currently. So
there's a simple explanation for that, and that's that model-based reinforcement learning still like learns them. Like if it needs to learn the models, then it still needs to learn something inductively. So if you haven't seen a state, your model will not be able to predict the state.
So you need to learn models that generalize. You need to, but even if you have that,
exactly,
it's still like doing planning over long horizons in a stochastic environment. That's still an unsolved problem.
Exactly. Like you can think of it like that. Sorry.
Yeah. So I think it's a very promising future direction for generalization, but yet there is several problems that need to be solved, open problems with model-based RL.
I think a couple of things that one needs to distinguish is like what kind of case of like how far out of the distribution am I? If I am like, for example, there's a difference between a case where you see a new state that you have never seen before, and none of your models has seen this particular input before, and none of your models will be able to say anything about this input. So in that case, you're just like screwed. But there's another case in which your models actually have like a reduced input space, and you can have a situation where like you have never seen the combination of things that look exactly like this, but your models have seen like all their respective input parts of that thing already. So all of your models can be quite certain about their prediction, and the state might still be unseen by you. And I think this is the case in which model-based reinforcement learning could eventually shine.
Yeah, right. I think we have been talking about this. Sorry to cut in here. Go ahead, please.
No, I think it comes down to building in a prior ultimately that tells you how you can generalize. There is some work on that. There is a paper from Josh Tenenbaum's lab that builds theory-based models that have a prior. But yeah, I think ultimately it comes down to you have to build in a prior to be able to generalize to new situations.
Yeah, kind of like
if I can just quickly
go ahead.
Add. I guess I am just along the similar lines. I think I wonder if there's something in between, like something closer perhaps to model free, which better leverages the structures of the MDPs we're interested in solving, or just like certain symmetries between like the state space, action space, and reward function. It just seems like we should be able to do much more in terms of saying something like, okay, this action takes me to this state and it's good in this for this particular reward function, but this sort of like opposite action is bad and takes me to sort of like a bad state. And at least for like a sort of perhaps more limited class of problems where we know something about these sort of symmetries in the action space or reward functions that we want to solve, and we might be able to perhaps get I don't know, just get further by doing this. But yeah, I'll stop here.
Yeah, right. Thanks. Like so far, we have been talking about the different techniques aspect of this generalization in reinforcement learning. We have also compared specifically the generalization in reinforcement learning with that in supervised learning, right? I think we all agree that like kind of model-based reinforcement learning is a potential research direction. As in Microsoft research, we are also studying like ethical issues in artificial intelligence. So maybe I can ask our panelists one last question. Are there any ethical issues in this generalization in reinforcement learning?
So I'll start. So, like, yeah. So first, I really want to reiterate on that. As an employee in Microsoft, I'm just extremely proud on how far we go on caring about responsible AI, like across Microsoft for everything regarding machine learning, not only RL. So I'm just really being proud to see this effort. I mean, everything. I think it may be not known to external people, but we do have responsible AI board and all these things. So I'm really proud to share that. We do take this very seriously. And secondly, I want to say, like, I think many things for like privacy, fairness, and all these things when it comes to decision making, I think reinforcement learning share with many other domain. But I want to say, like, especially when it comes to social impact like applications, they need to be of even like people need to be extra careful about it. But the one thing I find reinforcement learning really have opportunity is that because a lot of this kind of fairness and privacy issue come from like a bias in the training data, like a fairness come like due to the training data bias. But reinforcement learning, especially online reinforcement learning, I think that's one domain where you actually can actively collect the data. And I think there is a lot of research opportunity there because then we can already considering like all these responsible AI questions during like the framework development, and I see that as a really interesting combination.
Yeah, so I would just say that I disagree a bit with Cheng. So I think like even though we think in reinforcement learning we are collecting the data, or the agent is collecting the data, that's not actually what's going on. Because in reality, you either have a simulator or you have to run safe reinforcement learning, which is something we didn't talk about today. And in the simulator case, you clearly have simulator bias, where I built the simulator, so all of my personal biases will be in that simulator. Like there's clearly then that if I'm training my agent on a variety of tasks, then I build the variety, the task distribution, so I create like my personal, or reflect my personal biases in that distribution. And if on the other hand the data is from real life, you can't choose what a real reinforcement learning agent would do, because the real reinforcement learning agent would just choose everything equally. But that will kill so many people. So you'd end up choosing the things that are safe, and the things that are safe are the things where you have the data. And where do you have the data? You have the data from the privileged people.
Depends. I mean, we definitely don't want to kill people, but I will say not all real life applications have the risk of killing people. but I see your point. I agree with that. But I how to say? I think this is something I think it's just an awareness issue. I mean, we definitely need AI safety in some way. But if there is a possibility in some domain, I do feel this is an opportunity.
Well, I think we are running out of time, and it's about like the right time to wrap everything up. So, any final questions here? No? Great. Okay. So, a huge thanks to all our panelists for the inspiring perspectives on generalization in reinforcement learning. And again, I'll give a bit of summary here. So in today's panel discussion, we have generally discussed the definition of generalization in reinforcement learning and how this topic could be related to any other research directions like multi-shot or one-shot learning. Our panelists also shared insightful thoughts on why generalization itself is critical to reinforcement learning, especially when we think of the applications of reinforcement learning in real world. We also touched upon the benchmarks that are suitable for this type of generalization. For such benchmarks, we also need to examine in what dimensions the generalization is taking place. And on top of that, we also compared the generalization in reinforcement learning with that in supervised learning. With our panelists' point of view, the generalization could be much harder than that in supervised learning. And because of this underlying sequential decision making characteristics here. And finally, our experts are also raised some ethical issues in generalization reinforcement learning. And if I understand correctly, as one type of deep learning methods, reinforcement learning itself also has these ethical issues that can be related to the data we are using to train the model and the task we are using to train the policy. So I think that's all for this today's panel discussion. Thanks again. We also thank the audience for attending this panel discussion. Thank you.